I will move on right away. Lecture 7, electric current. And this lecture is very short. I hope I will finish this lecture within this class. And this lecture kind of bridges between electrostatics and magnetostatics. Okay, electrostatics, what I mean by electrostatics was charges are stationary. Charges doesn't move, right? That's electrostatics. And then magnetostatics, if you think about magnetostatics, charges are actually moving, right? Because there is a current. Current means the flow of charge. But the current amount doesn't change as a function of time. Okay, that's the magnetostatics. So as I transition from electrostatics to magnetostatics, we will learn about electric current. Briefly learn about electric current. There's a distinction between electric current, like a convection current and conduction current. And convection current, I personally think that the distinction between these two are too important. But convection current is like the motion of charged particle itself. Like if somebody, let's say I have a sphere that is charged positively, okay? And if I throw this sphere to anywhere, then I'm basically creating a current, right? Because charged objects are actually moving. So that's like a convection current, the motion of charged particles. And conduction current is a little bit different because in conduction current, the medium itself is neutral, like electric conductor, like metal. But if I apply the voltage between two ends of a metal, then electrons flow, right? Only electrons move, and the positively charged atomic nuclei stays at the same position. So the net charge is anyway zero, right? Everywhere, but current flows. So that's like a conduction current, like what's happening in the conducting medium. So how is it defined? As everyone knows, current is charge per time, right? And then current itself is a scalar amount, but it's composed. It can be calculated from the vector quantity, current density, current per unit area, dot and ds. Of course, this is an area vector, and then take an integration for the cross section. And the current density is current per unit area, and then this can be easily calculated by multiplying the charge density times the velocity that this guy is moving. Okay, so charge density multiplied by velocity, then you obtain the current density, right? And then if you integrate current density for a given cross-sectional area, you get current, right? And then what's this I then? This I is just a type of a carrier. So what I mean is that there are many possibilities, like the conduction in a material can be done by electrons, but there are also holes, positively charged charge carriers. So like to take into account multiple charge carriers, we just like put I here, but you don't need to worry too much about this I thing. This is just a type of charge carriers. And then electric current. So this is one simple exercise of calculating electric current. And let's say here's electrons, like electrons of uniform number density n, flowing with a constant velocity u, which is z direction, and u0 is a constant. and find the current passing through hemispherical shell of radius A. Hemispherical shell of radius A. Okay. Then J is, as I said, rho U, right? And then what is rho? We only know the number density of electrons, but we also know that charge amount of each electron, which is minus E, right? So minus En is equal to rho, right? That's what we know. And then U is given. So we know J. And once we know J, then I is easy. I is, sorry, I'll use my pen. I is J dot ds, right? And then we can make the problem even more, even easier, because J is anyway parallel to AG, right? Because U is parallel to AG. And because we have a dot product here, we don't actually need to perform like complicated spherical integration. Instead, we can just take the area that is like normal to the Z direction, which is the cross-sectional area here, right? And then the solution becomes much easier. So the I is J amount times just pi a squared, right? So it's, again, J is a vector quantity that can be integrated to obtain I, which is a scalar quantity. And then in that integration, we have dot product. So the direction of the surface and direction of J, only the amount that is normal to the surface will be integrated. So this is this. It's pretty easy calculation. So do we have any questions so far? So far what we have done was I just gave you the definitions, like a definition of J, which is current density, and then I, which is current, and how they are related. I think it's not too difficult. And then we have famous Ohm's law. Okay, Ohm's law means this. Okay, current density is proportional to the electric field. And then the coefficient is called conductivity. Okay, so for a given E, for a given electric field, more current flows if conductivity is higher. So conductivity, the name makes sense, right? Higher conductivity means higher current. And then inverse of it is called resistivity, right? So conductivity and resistivity. And similar to epsilon, the definition of permittivity, conductivity actually also can be nonlinear and anisotropic. So in actually conductivity is a 3x3 matrix rather than a scalar number. But again, in this lecture, we focus on linear isotropic media where we can treat conductivity as just a scalar number. Okay, and here I have a few examples of a conductor, and you can see some of the example has really high conductivity, like silver, copper, gold has the conductivity reaching like 10 to the 7, 10 to the 8. But the materials known as insulator, like diamond, have conductivity of 10 to the minus 13. So the difference is 10 to the 20, which is extreme, right? And then in the middle, we have like something like, gallium arsenide or silicon, like semiconductors. And the conductivity of semiconductors, as you can see here, varies a lot. Like here, the range is 10 to the minus 8 to 10 to the 3, right? So even lower bound is much higher than the diamond, and even upper bound is much lower than the metals. But anyway, it's in the middle, in between, and then it spans a huge range, like 10 to the 11 range. And that is because this is semiconductor, and its conducting property depends a lot on its doping level. And you may not know what doping means. Don't worry, you will learn, like, I don't know, in some other classes, like in 물리전자개론 or some other classes. So here, what you need to know is that materials have a large variety of conductivity, ranging from 10 to the minus 13 to 10 to the 7 or 10 to the even 8, right? And then high conductivity material is called metal. Low conductivity material is called insulator. And then the materials in between is called semiconductor. Okay. And then here at this point, I think it would be instructive to compare the permittivity and conductivity. So permittivity, as I said, is connecting D and E. Okay. And more fundamentally, it connects E and P. P is polarization. So what permittivity tells you, permittivity is nothing but 1 plus chi, right? So what permittivity tells you is how the bound charges of a material respond to the applied electric field to form a polarization, right? So that's the meaning of the permittivity. That's the interpretation of the permittivity. So permittivity is typically defined for insulators, which have bound charges. And then conductivity is different. Conductivity is connecting J and E. So conductivity means how much of current flows when electric field is applied, so that it tells you the response of free charges to the applied electric field. So conductivity is typically defined for conducting materials like gold, silver, or semiconductors. But anyway, what's important is permittivity describes the bound charge response. Conductivity describes free charge response. So when electric field is applied, conductors allows you to, the materials with free charges allows you to have current. And then the material without free charges and only with bound charges will be just polarized, and there will be no current. And as you may notice, as you may understand, this is actually not an absolute thing, because nothing is 100% conducting or 100% insulating, right? So if you look at this chart, if you apply the electric field, even diamond, the representative insulator, still have some current, very, 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 very weak, so we ignore, but there is current. And then and vice versa. So conductor and insulator is just about a degree. It's not about like an absolute thing. There's nothing like no free charge or no bound charge type of thing. There only exists degree. And then the relation between permittivity and conductivity will become actually more complicated. And you will learn about this when we learn about electromagnetic waves, that permittivity and conductivity are actually very closely connected. It looks like a very different thing, like bound charge, free charge looks very different. But if you go to an AC, like AC electric field, then they are connected. And you will learn about this later, like when we learn about electromagnetic waves. But for now, this is fine. So the model for conductivity is called Drude model. So this guy Drude, Paul Drude, like thought about this conducting model. And this is also pretty interesting to know, because like you can ask the same question. We all know that material is composed of atom and electrons, right? And then if we apply the electric field, we know that the electrons will feel the force minus EE, right? That's the force. So if the electric field amount is constant, then what's constant would be force, the driving force, right? So without damping mechanism, electrons in metal will be just accelerated forever, because force is constant, not the velocity. So force constant means acceleration is constant. And then without damping, electrons, the speed of electron increases forever, right? So then he thought, okay, that's pretty strange, because it looks like if we apply the electric field, then the velocity of the electrons reaches to certain speed. So the speed becomes constant, not the acceleration, right? And then he came up with this idea of damping. Electron must be damped due to some mechanism. And then he thought that this is due to the scattering, like either by atom or other impurities. Electrons just, not go forever, but they're scattered. So it loses its momentum when it got scattered, right? And then he modeled this mechanism like this, the damping mechanism as like 1 over tau. And this 1 over tau thing is like, you can understand this like this: minus mu divided by tau. So mu, so mv is the momentum, okay? So the momentum will be initialized. Momentum lost will happen per every tau, okay? So momentum per time is what is called 충격량, like impact, which has the same dimension with the force. So he thought that like there is a tau which tells you the average time between collisions, which is called relaxation time. And then if we have this relaxation time, then every tau, on average, electrons loses its momentum. Okay, so if you add these two, right, and then in a steady state, these two forces kind of balanced. And then when they are balanced, it's zeros. And then from that, we have U, which is a kind of terminal velocity. And then that should be tau E divided by M E. Kind of makes sense, right? And then from this, what you can do is, we know that J is rho V. And then rho is Ne minus Ne, right? Electron, so N is electron number density, E is the charge amount, elementary charge. And then U, the terminal velocity, we have here, the formulations here. So putting everything in, we have this relation. J is proportional to E, and the coefficient is Ne squared tau divided by M. And then he claimed that, okay, this should be conductivity. So conductivity should be written in terms of mass of an electron, elementary charge, and the number density of electron, and collision time by using this. It's very simple theory, but it fits to the experiment very well, actually. So it's pretty powerful analysis. Okay, so this I just brought this to you just to tell you that there is a interesting theory about the conductance. which is called a through-day model. And then the through-day model will become, you will learn about this also again in semiconductor classes too. So I'm not gonna go into detail about this. So once you have, so another thing, aspect we want to learn about the current and the charges was that here, a few important equations. So the equation of continuity is given by this. So the current is minus dq dt, like the charge, the charge loss per time at a given volume, and then q is rho dv. So you can write this equation like this, and then the time dependence only applies to the charge density, not the volume. So it's gonna be like this. And then this equation is actually same. Like if you go back to the original I, this is equal to j dot ds surface integration. And then if you do the j dot ds surface integration for a closed volume, by applying the divergence theorem, you have this relation. And then by equating these two, you get d rho dt plus divergence of j is 0. This equation is called equation of continuity. Okay, why this is called equation of continuity? That is because, like if you have some small volume, okay, and then let's say your d rho dt was negative. Okay, so charges are disappearing here. Then of course there should be current flow associated with it, right? The charge amount decrease at certain position. That means current flows outward. So this guy and that guy must be related. So the negative charge, the decrease in charge amount should be associated with the increase in current flow, right? So that's called continuity of charges. And then in steady state, interestingly, steady state means the d rho dv dt is 0. Then so the charge density doesn't change as a function of time. Then divergence of j is 0 too. Okay, and then divergence of 0 again means j is sigma e, and e is negative gradient v. So if you just do this chain of equations, you will get to the conclusion that Laplace equation holds. Okay, so this is important, another important conclusion, because here we are not assuming charges are stationary. Charges are moving around because we have non-zero current. But as long as the current flow is stationary, right, which is defined like this, the charge density doesn't change as a function of time, then Laplace equation still holds. So in terms of obtaining potential and electric field, we can use all the techniques that we used for electrostatics because Laplace equation holds for steady current. Okay, and then another interesting thing that we can draw is the Kirchhoff's law. So like going back to this equation, like a steady state equation, and then make it into a summation form again, like a area integration form again, it must be 0, which means the total current in a closed volume going in and out to the closed volume must be 0 in steady states. So that's the famous Kirchhoff's law. You probably learned this in your circuit class, right? So that means like if we set a certain volume, closed volume, in a steady current condition, the net current, like going out, or going in, if you make a summation of all current component, it must be 0. Okay, so like if the current 1 is coming in, current 2 and 3 is going out, then I1 is equal to I2 plus I3. This is nothing but the Kirchhoff's law, and then this Kirchhoff's law can be obtained or derived from microscopic viewpoint, as you can see here. Yeah. So do you have any question regarding this? So I have only like few more slides to go, like 2-3 more slides to go, and another thing that I can tell you about here, like the one appears in this slide is not that important, but anyway, from the equation of continuity, and then we know that J is sigma E, and then we also know from the Gauss law, divergence of E is rho V divided by epsilon, right? So we can write the equation only for rho. So the equation of continuity now converted to equation for the charge density. Okay, and then assuming that at a certain position in time, a certain position in space, the charge amount was rho 0, and then as time goes by, this charge amount should decrease exponentially, and then that exponential function can be obtained by solving this equation, and then the exponent, like here, is called a relaxation time, which is the ratio between epsilon and sigma. And this is like the time it takes a charge placed in the interior of a material to drop to e to the -1 to its initial value. So this part is not that important. It's just to tell you it's another form, another way to write equation of continuity. And from here, we can obtain one important value about the relaxation, about the material, relaxation of charges. Okay, so if you have questions, like don't hesitate to type in the chat. Okay, I'll just go ahead, and then I'll just come back if you have if your question appears. So the final thing, probably the most important thing in this lecture, the concept of the resistance and the power consumption. Okay, and the resistance, like as we learned previously, capacitance is defined as a ratio between Q and V, right? Resistance is a similar thing. Resistance or conductance. Conductance is the ratio between I and V. Okay, so when we apply some potential at two ends of one conductor, then how much of current would flow? And that's the conductance. It's similar to capacitance, right? When we apply the voltage between two conductors, how much of charge we can store? That's the conductance, and that's the capacitance, and the conductance is I divided by V, and the resistance is the inverse of it, V divided by I. And then we know the definition of V. V is E dot dl integration, right, at two ends. And then I is J dot ds, and J is sigma E. So from this, what you know is that if we know E field distribution everywhere, then we can easily obtain the resistance. The situation was same for the capacitance. Once we know the electric field distribution everywhere, then that's it. Then we can obtain the capacitance. Here, the same thing applies. And then regarding the power, you probably heard about this, P equals this thing. This thing is probably a pretty famous equation, like power consumption of a resistance is VI or I squared R. And this is obtained from this, like power is force times velocity. And then force here is rho E. Okay, rho E is the microscopic force, right? Rho is the charge density, and then E is the electric field. And then if you multiply the U, which is velocity of the charges, this is the power, okay, power density. And then you rearrange the term, like E here and rho U here, then it becomes E dot J, okay? So E dot J gives you a power density, and if you take the volume integration, you get the power. So as a very, very simple example, you can think about a conductor having a uniform cross-section S and length L. So uniform cross-section S and length L. Then you can easily calculate the resistance from this relation. So because it has uniform cross-section and length L is given here, and then it has a uniform cross-section, electric field must be uniform inside, so it's EL. And then sigma ES is just a sigma ES, because S is also uniform. EE canceled, so L divided by sigma S is defined, is actually the resistance of this rod, of this rod. And the power also can be calculated from this relation, and you can realize that this power is actually VI or I squared R, the equation that you know from circuit theory. Okay, so finally, what I want to cover is to obtain the resistance of a conductor, of a given conductor, but has non-trivial shape, like this. So this problem is exactly same as the problem of cylindrical capacitor. Okay, but instead, what we want to calculate here is if we apply the voltage V between inner conductor and outer conductor, and then assuming that the material inside is not insulating, it allows you to flow current. Okay, then the current flow will occur like this. So I want to calculate the resistance of a coaxial cable of length L. So that's what we want to calculate in this problem. Okay. But as I said earlier, Laplace equation still holds for stationary current. So if you apply the potential V, then the potential distribution must be same. Like in this resistance case or capacitor case, as long as you have the same boundary condition, the solution must be the same. Okay. So here, how the way you solve this problem is this: you first set potential 1, V equals 0. Okay, it's the other way around. Anyway, one potential, like zero potential at one cylinder, and then potential V naught to the outer cylinder. And then, as I said, Laplace, since the Laplace equation holds, you can just solve the potential distribution by solving the Laplace equation. And you know many ways to solve Laplace equation. That's what we learned in our last lecture note. And once you get the potential distribution, like this is the solution, then you can get the electric field by taking the negative gradient of potential, right? And then once you have the electric field, you can obtain current. Current is J dot ds, and then J is sigma E. So if you know electric field, then you can just perform integration. And then in this case, the surface area is here, the side of the conductor, right? Because it's how the current flows. But it doesn't matter kind of which type of surface you choose. So for instance, you can choose this type of a surface and then calculate the current flow passing through the surface area. But then the problem would be just more complicated, whether the answer would be the same. So I would recommend you to deal with the area with the same symmetry to the system. Then you can easily calculate the current, which is this. Okay, and finally, by taking the ratio between current and the potential difference, V naught, you get the resistance. Okay, and the inverse of it is conductance. So what I wanted to tell you is the resistance, getting resistance and conductance are basically fundamentally same as obtaining the capacitance of the problem. So in order to obtain the capacitance of a given structure, you need to know the potential distribution or electric field distribution everywhere. And once you know that, problem solved. The only steps left are just taking integration. And same here. In order to obtain the resistance, you also need to get the electric field distribution. And for the stationary current, because Laplace equation holds, the way you get the solution is basically the same. Okay, so it was a little bit hasty, but anyway, I wanted to finish this before we move on to the magnetostatics after the midterm assignment. So if you have any question, please ask. Hang Jinung asks, Drude model requires, does Drude model require uniform electric field assumption? This is a very nice question. This is a very nice question. And yeah, I would say it will be more convenient to assume that way. Yes, yes. Each of the equation actually holds without that assumption, but the one step that I'm a little bit uncomfortable is this, like taking the average time between collisions. So in order to take average time between the collisions, it would be more reasonable to assume that the electric field is homogeneous everywhere. so that the collision probability is also homogeneous everywhere? This is a nice question. I would say yes, not necessarily, but yes. And Park Jun asks, in the last example, since current flows from inner cylinder to outer cylinder, does the charge of the inner cylinder slowly decrease? No, no. So this is another thing that you can be easily confused. But the situation that we are dealing with is the case where we supply the charges by using battery, right? So the fact that potential between these two positions are held at a constant means charges are supplied by the batteries. So there's no charge, this charge amount change as a function of time. And that's a necessary condition for the stationary current. So if you're correct, Park Jun, like let's say we take charges, take the battery off, then of course there will be charge flow associated with current. So the charge at the center cylinder should decrease as a function of time. Then the voltage between the outer and inner cylinder must also decrease, right? So it becomes a time-dependent problem, right? So that we cannot use Laplace equation anymore. Yeah, but this is really good question though. Anything else? Okay, so now it's time to stop.